little bit of the history and the foundation on which he was building those laws. So when we're talking about motion, who was the first individual that you guys read about in there? Aristotle. Aristotle, and he was around in what years? All right, so the 300s BC, yeah. So early 300s BC. All right, now Aristotle's a significant individual because he was really the first one to give us any kind of laws of motion, and the ancient Greeks were really the first ones to give what we now recognize as modern science. They were trying to actually provide reasons and trends in the world that they observed. And Aristotle, I was able to identify a couple of things. First of all, one of his laws of motion would have been that it is the natural tendency of all objects to come to rest on the surface of Earth. It is the natural tendency of objects to rest on the surface of Earth. And he stated this because anything that he ever saw that was moving always came to rest. What's up? Okay. Didn't matter what it was, it would eventually stop. The other part of this is everything that went into the air always came down. Didn't matter if it was thrown, shot, a bird, it was going to come back down to Earth. So without actually recognizing it, what couple of forces do you think he would have been really observing here? Definitely gravity. And what else? So gravity is going to be the one that makes things come back down. What's going to be the one that makes things stop? Inertia is not a force. Other thoughts? What makes things stop? Friction. Excellent. All right, so really, without realizing it, Aristotle was identifying gravity and friction. Now, the other part that he would have identified was that for objects that come towards the ground, the heavier an object is, the faster it fell towards the ground. Heavier objects fall faster than lighter ones. All right, so Aristotle would never have witnessed anything that went up and didn't come down. He never would have witnessed anything that started moving and didn't stop moving. So his first law there makes sense simply because he didn't have any evidence that was contrary. His next one, he was taking a large amount of observations. First of all, he was thinking about the idea that if he holds a heavy object in one hand and a light object in the other, this one seems like it has a greater tendency to drop towards Earth. It feels like it's going to try to go down. In fact, if I try to lower my hands at the same rate, this one seems like, or let me rephrase that. If I apply equal resistance with both hands, this one's going to go down faster. Well, and then if we take them, and we take both objects, and we drop the objects, which one's going to hit the ground first? Clearly both. So, Aristotle's set of observations here all make good sense. They all seem to be well-founded. And in fact, they're well-founded enough that they stick around for almost how long? 2,000 years. Which is when we get our next individual, Galileo. Now, Galileo, he has two real contributions here. First one is that he is allegedly tested one of these, and allegedly he went to the top of the Leaning Tower of Pisa and dropped a heavy ball and a light ball, and what happened? They fell at the same rate. So, allegedly tested a heavy ball and a light ball, and found that they fell at the same rate. They fell at the same rate. Okay, so what we really were talking about with Aristotle, and he didn't realize it, Aristotle didn't understand this, but air resistance is a force. Air is going to push back on anything that's moving. So if we want to talk about a heavy object and a light object, and I can remove the air from pushing back on the system, I can make this piece of paper in this book drop at the exact same rate. So simply by removing air resistance, if you watch the paper, it drops towards the ground at the exact same rate as the book. Alternatively, I could probably just crumple up the paper, and it would yield the exact same results, both falling towards the ground and hitting the ground at the exact same time. For those of you who are still questioning this, we tested it on the moon where there is no air. It works. So that's the first part that Galileo did. But what was actually more important is, in addition to coming up with this idea, he also then branches out and talks a whole bunch about, how the sun's the center of the solar system. But this was all very important for allowing others to follow him. The work itself was pretty big, but more importantly was the cultural context. So the early Greeks were the ones who really set the foundation for modern education. They were the first ones to really try to explain things and then teach it to other people. And if we scroll forward those 2,000 years, 1400s, 1500s, 1600s, who was in charge of education in those periods? 1400s, 1500s, 1600s. Who was in charge of education? Say again? The Catholic Church. So the Catholic Church was in charge of education, and they were teaching Aristotle. They believed Aristotle had some good findings, and he did, and he had some solid evidence. So the Catholic Church taught Aristotle. And Galileo is saying, hang on. Aristotle's wrong. How would that have been received? Why not very well? Because the church comes out and says, hey, this is how the world works. And Galileo says, no, what you're teaching is wrong. How does that sound to a group of individuals who, set fire to people who disagree with them or who preach heresy? Sounds not good. So Galileo really had a big issue here because he was trying to go not just against Aristotle, but against the Catholic Church, because they were teaching Aristotle. So Galileo wound up being tried for heresy and convicted of heresy. And he did kind of get off the hook a little bit because he was buddy-buddy with the Pope. So he cut him a break, and instead of burning him at the stake, put him under house arrest, which for Galileo, that's not terrible because his house was pretty big on an orchard. And he really wasn't going to go anywhere because in his older age, he'd gone blind because he kept staring at the sun through a telescope. So, it's not that bad. Big house, orchard, you can't go anywhere really because you're blind. House arrest isn't too bad. So, he set the groundwork.
If he was blind, how did he see his work?
He did a lot of his work beforehand, and he had some assistants. He actually wasn't allowed to work after he was convicted of heresy. He set the groundwork for others to challenge Aristotle. All right, that's when we get Newton. Now, Newton doesn't have to worry about challenging the Catholic Church for two reasons. One, Galileo's already kind of done that. He's gotten that taken care of. Two, he lives in England, where if you've gotten to that part in your history classes, they don't actually follow the Catholic Church at that point. They follow the Church of England, so he's off scot-free. So Newton comes around, and he gives us a set of laws of motion. These are all based on observations that he's made and things that he's found to be true. Newton's first law, what is it? Object in motion stays in motion. All right, an object in motion stays in motion. Let's go ahead and write this one down. An object in motion stays in motion. And an object at rest stays at rest. Object at rest stays at rest unless acted upon by an outside force. By an outside force. All right. This law also has a nickname. What's the nickname for the law? Law of inertia. Excellent. Where inertia is simply an object's tendency to resist a change in motion. Now, inertia is also tied to a quantitative property that you can measure about objects. What property is inertia? What could you measure that would be inertia? Mass. Mass is inertia. More mass, more inertia. Less mass, less inertia. And now I've got stuck in my head a set of lines from a book. So one of my friends got Lachlan a book titled Newtonian Physics for Babies. And it starts off with like, this is a ball. The ball has mass. More mass, less. I'll have to bring it in and read it to you guys. It's pretty good. All right, so we've got this law of inertia. Now, we can demonstrate this, and you guys have probably actually seen this demonstrated before, where you take a tablecloth and you whip it out from underneath a set of glasses, and the glasses stay in place. No? Okay, well, I didn't bring in glasses because I didn't want to pull a Logan and shatter glass all over the floor. So instead I brought pennies, and we're going to treat the pennies as though they're the glasses, and we're going to treat a note card as though it's the tablecloth. Okay? So the way it would work is with the tablecloth, I whip it out from under the glasses, and the glasses would stay in place. And the reason they stay in place is because in order to get something to move, you need a force. Now, with the note card here, I can just slide it around slowly, and the pennies stay with it, right? Well, they stay with it because the force of the note card on the pennies is allowing them to accelerate. That's going to get us into the second law in just a moment here. But if I move the note card too quickly, the pennies don't have enough time to move. They don't have enough time to accelerate. And instead, they just drop straight down. Because they have inertia, they have a tendency to resist a change in motion, and therefore don't move with the note card. Now, I do want to demonstrate this a little bit larger, but again, since I don't want to risk breaking glasses in class, I've got a video instead. Now, in Newton's first law, we said that an object at rest stays at rest unless it's acted upon by an outside force. So for Newton's second law, he tells us what a force is. Anybody happen to find the definition of force in their reading? No. Anybody? What do you got, Kendall? Okay. Okay, so that's Newton's second law. The acceleration of an object is always in the same direction of a net force. Do you have what a force is, though? No. Yeah, Rory. Push or a pull that acts on an object. So a force is a push or pull. Excellent. Now, mathematically, we can express what Eva just said as Newton's second law, which is F equals ma. showing that the net force on an object, net force, so the total push or pull, is equal to the object's mass times its acceleration. Now, mass is, of course, measured in kilograms, and acceleration is in meters per second squared. So we could talk about the force as being measured in kilogram meters per second squared, or we could not. And we could use the unit that Newton gave us, the Newton. So force is measured in newtons. And in the English system, what is force measured in? Pounds. Guess? No? Okay.
I mean, Jackson said it, but he didn't say it loud enough.
Oh, okay. All right. So measured in newtons in the metric or SI system and pounds in the English system. All right. Now, when we are talking about forces acting on something, one of the tools that we use to illustrate forces acting on an object is called a free body diagram. Free body diagram. So when we talk about the Dice's model, and the first step is draw, this is why draw is actually an important step. So let's go ahead and talk about the tablecloth we just saw. Here's my table. I'll grab another color here. Here's my tablecloth. And that was attached to a motorcycle. All right, let's get my motorcycle here. So clearly I can't draw motorcycles or bicycles. There, that looks about right. And we have a rope attached here. All right. What forces, what pushes or pulls acted on the tablecloth? What? The motorcycle. All right. So I've got the force of the motorcycle. Did anything act against the force of the motorcycle? The answer is yes, and I heard it a couple places. But then we have to identify what. Say it again. So what would pull back? What would try to resist the motorcycle pulling the tablecloth forward? Say again. Weight. Stuff on top of it. Okay. How would it do that? What kind of force would you identify? Possibly that you read about. Friction. So friction is going to act back. And I'm going to write force of friction. So friction is a force that exists between any two objects in contact. Okay? And friction always resists motion. Always tries to make things stop or make sure they don't start moving in the first place. All right? Now, in this situation, so far we've been able to identify a force that is acting left and one that's acting right. Are there any other forces that are acting on the tablecloth? Gravity. Force gravity. Now, in a free body diagram, we showed not just the presence of forces, but also the size of forces. Because forces are vectors, meaning they have both direction and magnitude, we draw the arrows so that the one that has more force is a larger arrow. Now, we know that the motorcycle must have had more force than the friction, otherwise the tablecloth couldn't have accelerated forward. Okay? But in this case, we must also have something acting against gravity. What would act against gravity in this case? Revolutions. What would act against gravity? What would push on the tablecloth? Let's look at a simpler system. We've got a box. Take the box and set it on the table. Gravity's acting on the box, right? Now, if gravity is the only thing acting on the box, that box goes through the table. Okay, that's not happening. So something else must be acting on the box right now. Say again? The table. So the table is exerting a force on the box. Meaning that in our system here, talking about the tablecloth, that must mean that the table is pushing up on the tablecloth. And we call that a normal force. So force normal. You okay there? Okay. Gotcha. All right. So, a few things we can identify here. First of all, looking at the motorcycle force and the frictional force, the motorcycle must have a greater force, and therefore we can accelerate forward. The normal force and the gravity force must be equal. If they're not equal, then the tablecloth needs to either be thrown into the air by the table. I don't see that happening. Or the tablecloth needs to crush through the table. I also don't see that happening. So since the tablecloth is neither being tossed into the air by the table nor crushing through the table, the force normal and the force of gravity must be equal. Which brings us to talking about net forces. A net force is the total force acting on an object. The total force acting on an object. So what value of net force would you say would be acting vertically on the tablecloth? What value of net force would you say is acting vertically on the tablecloth? Zero. Because if it's a positive number, it gets thrown into the air, and if it's a negative number, it crushes through the table. So zero net force. When there's zero net force, there's zero acceleration. Zero net force is zero acceleration. All right, another example we could talk about. Your car with cruise control on. When your car is driving down the highway and you've got cruise control on, what kind of force pushes you forward? What's the cause of the force pushing you forward? Why does your car go forward? Give me one more step after that chain. Sure, the wheels are moving. The wheels are rotating and pushing the car forward. What's trying to cause the car to stop rolling forward? Friction and maybe some air resistance. I'm not talking about hitting the brakes and the gas at the same time. That's a bad decision. I'm talking about hitting the gas, and why don't you just keep going faster? You don't keep going faster because when you turn on cruise control, yes, your engine's trying to get you to go forward. But you also have the wind resistance and the friction pushing back. So you still have forces acting on it, but they're balancing out. And the net force between them is still zero. You have zero net force, even though the car is moving. It just can't accelerate. Okay? So an idea we need to make sure we've got is that objects can move if they, even if they have forces on them, they just can't accelerate if the net force is zero. Okay? Questions about that idea? Okay, then I've got three additional forces that we need to identify. So we talked about the force of the motorcycle. We get it, the motorcycle's pulling the tablecloth forward, right? We also need to talk about what are these three. Well, let's start with the easy one. Force of gravity. Force of gravity is how much the Earth is currently pulling on you. We can calculate the force of gravity, as being equal to mass times gravity, where gravity is the acceleration we experience on Earth. which is, 9.8 meters per second squared. So every object we drop, and here's where Galileo comes back, every object we drop falls towards the surface of Earth at 9.8 meters per second squared. If you jump off a cliff, you're going to fall towards the ground at 9.8 meters per second squared. After the first second, you'll fall at 9.8 meters per second. After the second second, you'll fall at 19.6 meters per second, and so on. Okay? So the acceleration due to gravity is 9.8 meters per second squared. Acceleration due to gravity. This is different from the force of gravity. Acceleration of gravity, force of gravity. Force of gravity is your weight. While all objects accelerate at the same rate, all objects have different weights, and their weight depends on their mass. So, for example, I have a mass of about 110 kilograms. I am accelerating towards Earth at 9.8 meters per second squared. Therefore, when I plug this into my equation for force of gravity, I find that I weigh 1,078 newtons. So I have a weight of 1,078 newtons. The force of gravity acting on me is 1,078 newtons. Brooklyn and I have the same acceleration due to gravity. We are both falling towards Earth at the same rate. However, I am willing to venture that we do not have the same weight. You would agree? Okay, good. All right. Questions about force of gravity. Next one on my list. Normal force. Normal force is a force that exists between two objects in contact that is perpendicular to their plane of contact. A force between two objects in contact that is perpendicular to their plane of contact. To the plane of contact. So if we go back to talking about the box sitting on the table, gravity's pulling down, the box is in contact with the table. Because the contact between them is the plane that matches their surfaces, then that means the normal force must act perpendicular to that, or straight up. Okay? And the last one we've got to identify is friction. Friction is a force that opposes motion. A force that opposes motion between contacting surfaces. That opposes motion between contacting surfaces. There are two types of friction that we will be talking about. The first type is kinetic friction. And the second type, notice I left some space here, is static friction. All right, so things we talked today. A little bit about Aristotle and what he thought about motion. We then talked about Newton's first law, an object in motion stays in motion, an object at rest stays at rest unless acted upon by an outside force. We defined Newton's second law, telling us what a force is and that F equals ma. We then showed how to draw free body diagrams and what net forces, normal forces, friction, and gravity each were. Now, we actually just covered more topics in this one section than are in the entirety of chapter 11, which we just finished. So, needless to say, this is a lot more intense chapter. So if you need to read the rest of that section tonight, I would strongly suggest it. Okay? Now,